Hi, welcome to VTeach. Now we'll be dealing about space wave propagation, where we had seen so far the ionospheric propagation as well as ground wave propagation. So the last concept or the third mode of propagation is space wave propagation. Here it is always limited to line of sight distance itself. Line of sight distance is nothing but the distance between transmitter to the receiver, and the transmitter should always see at least the top of the receiver, and it is always limited to the curvature of the earth. So as I said, when the distance is been passing from a transmitter towards the receiver, it should be minimum distance, and line of sight propagation will be limited to a few kilometers from the earth surface. So always it will be in observational point of view from a transmitter height to the receiver height. So here always the antenna height is been the most important parameter when we use line of sight propagation. And coming to this range of space or line of sight distance, what is that is, it is always the slightly the space wave communication is possible only beyond the line of sight distance, and it is always, as I said earlier, it depends upon the heights of the transmitting and receiving antennas. Let me consider the distance between the transmitter and the receiver be d, and the heights be ht and hr respectively above the ground, and the distance will be, the line of sight distance will be now becomes as d1 plus d2. So what is that d1 plus d2 is that here I had taken two antennas. So you let me draw this diagram for you once again to understand better understanding. So a curvature structure has been taken in which I has taken two antennas. One is the transmitter antenna with having a height ht, and the other one is the receiving antenna having a height hr, and I am been touching the line of sight here from A to C. Whatever the signal that is been crossing, it just grazes the earth surface. Remember, this is called grazes the earth surface. And here if I draw that virtual distance, I'll be having the mid region as origin point 0, with having a distance r from either transmitting or receiving distance. And if I calculate the distance from the origin to the transmitting antenna as d1, and if it is from origin to receiving antenna as d2, then the total distance, line of sight distance, will be d1 plus d2. That is what I had mentioned here. So above the ground surface I has taken the origin point as b, and at transmitter I has taken it as a, and at receiver I has taken it as c. Now I am going to calculate the radius of earth from these two triangles which are been formed. So I am going to calculate the radius. It means that I need to calculate this part. So triangle OAB and triangle CBO will give me the exact radius. So in what way it could be designed is that I know this particular distance d1, I know this particular distance r. What will be the hypotenuse? Then I'll be having d1 equal to ht, here as it is d1 equal to ht plus r, means the total length I has taken ht plus r whole square minus r square, because I want to calculate only till this region, but I am availed with ht plus r value, so I am separating it. So ht plus r whole square minus r square, so I'll be having d1 as square root of 2r ht, and similarly d2 also I'll be having square root of 2r hr. As the distance, line of sight distance is d1 plus d2, I am adding both of them. That is square root of 2r ht plus square root of 2r hr will be equivalent to square root of 2r into square root of ht plus square root of hr. So in simplification, generally we will be considering the ideal case as 6370 is the minimum radius. So here the distance will be 3.57 into square root of ht plus square root of hr, and this is the line of sight distance. Remember, this is line of sight distance between antenna, transmitting antenna to the receiving antenna. Now moving on to the effective earth radius. So this effective earth radius is observed when we follow a path which has a slight downward curvature due to refraction. So right now I am seeing this in the same diagram. A curvature structure is been taken, and let me take it, this is a vertically polarized signal, and now this signal is being deviated due to some refraction, and this deviation is been occurred, and obviously we will be having a certain loss of the signal due to this curvature, and slightly it reaches beyond the horizon, and this is accountable if it is bit greater in the atmosphere. So what is that is, we need to consider the same expressional view and find it out the relation. Remember this diagram, I am been calculating the same expressions for this. So for the convenience sake, I will be drawing the diagram for you. So Earth's curvature, from Earth's curvature I need to consider the relations. So here I have taken h and dh. So this is one, where I will be having h plus dh is the total length, and another one is r. So I will be having the total length as r plus dh. Now the variation is considered to be as u of dt, and now I will be taking the points which I have taken, that is, and this is r. So this is the view of the diagram with the help of this I am going to calculate or derive the radius of curvature. So here the radius of curvature, if we consider when traveling nearly horizontal in the troposphere region, and the path is going to bend into an arc with refractive index with reference to the height. So let me consider v is the velocity of propagation and h is the height of the earth above the earth, and r is the radius of curvature. Capital R is the radius of curvature and r is the actual radius of the earth. Now angle is always given by arc by radius. So it will be d theta. This is the arc here, which is given by v dt by r. And now what is that is, so similarly I will be having r plus dh into d theta plus v plus dv. So this is v plus dv. This is the deviation. So v plus dv dt. So this is the below layer I am considering, this is the above layer that I am considering to find it out the curvatures. And now I am going to subtract the both the regions. So r plus dh minus r into d theta equal to v plus dv minus v into dt, which gives me dh d theta equal to dv dt, or else d theta by dt equal to dv by dh, where v is considered to be as c by square root of Kr, or else C equal which is C by mu, where Kr is the relative dielectric constant and C is the velocity of the light and mu is the refractive index. So while changing the refractive index with height is obtained by dV by dH equal to minus C by mu square d mu by dH, where I will be separating this C by mu square in this way, C by mu into 1 by mu into d mu by dH, where I will be calling it as minus V by mu, because C by mu is nothing but V. So minus V by mu d mu by dH. So V equal to C by mu. So I am substituting here. So I will be getting that. So dV by dH is approximately minus dV d mu by dH. And as R d theta equal to V dt, we will be having R equal to minus dH by d mu. So these equations shows that the radius of curvature is a function of rate of change of dielectric constant or reflective index with height changes from hour to hour, but in practice an average value 4 times that of the radius of earth is used. So simply we can say this: the radius of curvature is a function of rate of change of dielectric constant or refractive index with the height changes from hour to hour. In general, it is 4 times that of the Earth's radius. For a standard atmospheric refraction, the Earth's radius is 4 by 3 times that of actual Earth radius. Now, what is the effect of this Earth's curvature on tropospheric propagation? So there are certain effects that are going to be happen with the Earth's curvature while tropospheric propagation is being considered. That is, the difference in path length is going to be reduced. The difference in path length is going to be reduced for reflected waves, as point of reflection on ground is going to be raised. So which reduces the signal strength. And the second point is that reflection at the ground takes place at spherical point rather than at flat point, and it always gives a divergent which results in weaker at receiving point. So this tends to increase the field strength of total space wave. So these two effects are being produced by the curvature of the earth, which are of opposite in nature, and there is no neutralization in each other. Thank you.